Interested in learning more about how our TempRite CPVC can improve the performance and properties of your PVC products? You've found the right place. Discover the countless benefits of using TempRite CPVC in your PVC blends and how it can help you make your products exactly what your customers are looking for. First, we would like to introduce ourselves. Owned by Berkshire Hathaway, we are part of one of the world's largest public companies. Berkshire Hathaway is ranked number 4 overall on the Fortune 500 list of U.S. companies. Located in Omaha, Nebraska, Berkshire Hathaway owns about 60 businesses in several different sectors across the globe, totaling $247 billion in revenue in 2018. These sectors include insurance and financial services, utilities and energy, manufacturing, service and retail. With involvement in many sectors, Berkshire Hathaway was attracted to Lubrizol for both its unique and comprehensive portfolio chemical additive technologies and advanced specialty polymers. Lubrizol is a truly international corporation with global yearly sales of $6.8 billion, thanks to more than 8,650 employees. We have a global presence of technical facilities, manufacturing sites, and sales offices that make both our product range as well as our technical and sales support easily available for all our customers. Lubrizol's portfolio is divided into 2 separate divisions: Lubrizol Additives, which specializes in supplying lubricant and engine oil additives, and Lubrizol Advanced Materials, which produces specialty polymers and coating technologies. Those are used in a wide variety of applications, including everything from personal and home care to engineered polymers and performance coatings. TempRite CPVC is one of the specialty polymers Lubrizol produces in the United States, Belgium, the Netherlands, India, and Thailand. Now that you've learned a little bit about Lubrizol, let's explain what CPVC is and how to blend TempRite CPVC resin with PVC. For 2/3 of its resin weight, CPVC consists of salt and only 1/3 comes from petroleum resources. CPVC can both be down and recycled. Many local standards allow the use of CPVC recyclate. It is compatible with PVC and can be integrated into circular economy efforts. PVC resin contains up to 57% of chlorine, while the chlorine content in CPVC resin, post-chlorinated PVC, amounts up to 67%. The higher chlorine content in CPVC results in the material being more rigid and having a higher thermomechanical performance compared to PVC. At first glance, our CPVC production may seem complex. However, you will notice how streamlined our process is to ensure the safest, highest quality end product. To produce CPVC, we purchase PVC resin, place it through a post-chlorination process to increase its chlorine content and obtain CPVC resin. The post-chlorination process enables CPVC to have a higher temperature resistance than PVC. To obtain 100% CPVC compound, various additives are compounded into the CPVC resin. The CPVC compound is used by our customers to make pipes, fittings, valves, tower packings, sheets, welding rods, and other products that are molded or extruded for use in high-temperature or highly corrosive environments. Those products are present in a broad range of applications, from hot water distribution to metal plating, chemical processing, and fire sprinkler systems. The major benefits of CPVC compounds and resins are high heat resistance, high Vicat softening and heat deflection temperature, high resistance against corrosive chemicals, high fire resistance, drinking water and food contact approvals. The use of CPVC resin as an additive in your PVC compounds will improve the material properties for both rigid and flexible PVC profile applications. With regards to the blending process of TempRite CPVC with PVC, our resins are designed for a high compatibility with PVC. They are easy to blend with existing PVC formulations and keep the processing of PVC CPVC blends user-friendly. The blending of CPVC into your PVC results in direct benefits of your blend. 1. Higher Vicat softening temperature. Depending on the PVC-CPVC ratio, the Vicat can be anything from between around 77 degrees Celsius, if 100% PVC, to around 115 degrees Celsius, if 100% CPVC. 2. Better flame and smoke properties. 100% CPVC compound has an LOI, limiting oxygen index, of 60, improving the flame retardant properties of the final product. 3. Low smoke density in case of fire exposure. Smoke development from CPVC-based products is extremely low, leading to a superior fire classification. 4. Better flame retardancy. The higher chlorine content is increasing its resistance to fire, while keeping its mechanical strength under thermal stress. 5. Higher modulus of elasticity. The more CPVC resin is added to the PVC blend, the higher the modulus of elasticity becomes, since CPVC is a more rigid material due to its higher chlorine content. 6. Lower shrinkage. Lower volume contraction during the cooling step when processing PVC-CPVC blended products. And 7. Increased flexibility. When adding CPVC to plasticized PVC, the mixture becomes more flexible, more soft, and hence less plasticizer is needed in the blend. With regards to the blending process of TempRite CPVC with PVC, our resins are designed for a high compatibility with PVC. They are easy to blend with existing PVC formulations and keep the processing of PVC-CPVC blends user-friendly. When blending TempRite CPVC into rigid profile applications, the addition of CPVC resin influences the process as such that there is only little modification on rheology necessary. Sometimes the addition of CPVC also results in a shorter gelation or plasticization period. When blending TempRite CPVC into flexible profile applications, the addition of CPVC resin leads to shorter and lower plasticization, a lower melt viscosity, a better melt homogeneity, and an overall improved appearance of the final product. When blending TempRite CPVC for rigid profiles, the CPVC impacts the modulus of elasticity. The more CPVC is added, the higher the rigidity of the final product will be. The addition of CPVC will increase the Vicat softening temperature. The higher the CPV content of the blend, the higher the heat resistance. Here is a comparison of PVC-CPVC blends based on two different CPVC resins, one with a K value of 60 and the other one with a K value of 57. The oven sag resistance test on CPVC proved that the more CPVC is in the blend, the higher is the heat resistance. Here, the profile stiffness versus elevated temperatures was evaluated. Here you can see a 1-hour test comparison on heat reversion. Once at 85 degrees Celsius, once at 100 degrees Celsius, comparing the performance of different PVC-CPVC blends. The more CPVC is added to the blend, the lower the shrinkage. CPVC compound has an LOI, limiting oxygen index, of 60. That means a product made from CPVC requires 60% oxygen in the environment in order to sustain a flame. Since our environment only contains around 20% of oxygen, CPVC has self-extinguishing properties and improves the flame retardancy properties of profiles. This flame retardant property of CPVC is also the reason why 100% CPVC pipework is allowed in fire sprinkler applications in building construction. TempRite CPVC was tested according to EN 13501 for its fire classification as a construction product and building element and has achieved the rating BS1D0. B is the rating of the fire behavior, and CPVC has low flammability and does not contribute to flash over. S1 means low smoke development, and D0 that there will be no burning drops from the product during a fire. We believe BS1D0 to be the best fire classification that a plastic material can achieve. In addition to the European fire classification, PVC blends containing TempRite CPVC can also achieve NFP flammability ratings. When using CPVC resin in the PVC blend, it won't be necessary to add any flame retardant additive. When formulating the blend, it needs to be understood that the type of impact modifier chosen for the formula will have a great deal of influence on the flammability rating of the final product. Following an example based on the French national standard, 100% PVC product will achieve an M2 rating, while a blend of 75% PVC, 25% CPVC will already be attributed a rating of M1. Glow wire testing is an example of the indirect flame method. Test results from applying these methods provide a way to compare the material's tendency to resist ignition, self-extinguish flames, should ignition occur, and to not propagate fire via dripping. The relevant sections of the IEC 60695 standard specify the details of the glow wire test to be applied to test specimens of solid electrical insulating materials or other solid materials for flammability testing to determine the glow wire flammability index, GWFI. The GWFI is the highest temperature determined during this standardized procedure at which the tested material does not ignite or, if it does, extinguishes within 30 seconds after removal of the glow wire and is not totally consumed by the fire. In addition, molten drips, if they occur, do not ignite the wrapping tissue. We conducted this test on a PVC TempRite CPVC blend in the ratio of 85-15 compared to 100% PVC and 100% PVC containing antimony trioxide as a flame retardant additive. The results shown on the left graph speak for themselves. The extension time was also evaluated and found to be 1 second for both PVCs, while again there was no extension time for the PVC CPVC blend. So it can definitely be said that profiles based on PVC CPVC blends do have an improved flame retardancy. The optical smoke density was measured according to ISO 5659 to measure how PVC, a PVC containing a flame retardant, and different PVC CPVC blends contribute to smoke development when exposed to fire. The flame retardant PVC shows only minimal better results than the regular PVC, while the different PVC CPVC blends outperform both of prior considerably. The higher the CPVC content in the blend, the less the smoke development. Here are some application examples of profile applications where CPVC will vastly improve the performance of the extruded products. Dark fencing, windows, shutter and siding. All of these products will be exposed to sunlight and require therefore a higher heat resistance. This is in particular important in hot climates where the ambient temperature can come close or even exceed the maximum performance temperature of a standard PVC. Electrical profiles. Depending on the region, national legislation may very well require a higher heat and fire resistance for conduits and profiles in electric and electronic applications. In many cases, standalone PVC will not be able to comply. Using a PVC CPVC blend instead will, however, contribute for the installed product to continue to comply with requirements, even if those become more stringent. Evacuation pipe. This concerns applications where the VICAT is required to be higher than 78 degrees Celsius, or even higher than 90 degrees Celsius, such as drain, waste, vent applications, which concerns MU-PVC solvent-welded waste systems. Particular for the UK market, additional standards can apply. 1. Specification for thermoplastics, waste pipe and fittings, MU-PVC, according to BS 5255, requiring a VICAT of more than 80 degrees Celsius. 2. Plastic piping systems for soil and waste discharge, UPVC, according to BS EN 1329, with a thickness of 3 mm, requiring a VICAT of equal or more than 79 degrees Celsius. And 3. Plastics piping systems for soil and waste discharge, chlorinated, with a minimum of 50% of CPVC, according to BS EN 1566, with a thickness of 1.8 mm, requiring a VICAT of equal or more than 90 degrees Celsius. Rigid calendaring of card applications. In order to prevent distortion of the cards under extreme conditions, various national standards may require a higher heat resistance compared to what standard PVC can perform. This concerns mainly SIM or TV cards, in rare cases also credit cards. When calendering flexible films and sheets, the addition of CPVC to PVC results in better printing quality. This is a picture taken 5 minutes after the calendering process for visual testing. Special inks with different superficial tension from 32 to 37 millinewton per meter were used and calendared on films based on different ratios of PVC CPVC blends, which contained 60 parts per 100 of rubber, PHR, of dioctyl phthalate, a general-purpose plasticizer. As one can see from the picture, the higher the CPVC content in the blend, the better the printing quality. Here is an example of where the printing test was done using Sublimely inks, the blend containing 60 PHR of DOP. The pictures were aged at 23 degrees Celsius for 30 months. The colour of the new picture on the 100% PVC film faded, while on the 100% CPVC film looks like new. The weldability of flexible calendared products, comparing 100% PVC and different ratios of PVC CPVC blends containing 60 PHR plasticizer, was evaluated. During the dynamometric test, a welding power of 0.8 kilowatts was exerted at different welding times, from 0.2 to 0.5 seconds, to observe the breaking mode. For the 100% PVC product, delamination of the weld occurred throughout, while for the PVC CPVC product, the welding quality improved the more CPVC the blend contained. With regards to the impermeability of oxygen, it was observed that the gas permeability properties improved with increasing content of CPVC in the blend. For this evaluation, a flexible calendared sheet of 1.5 mm thickness was tested with oxygen, carbon dioxide, nitrogen gas, and water vapour. When measuring the softness or shore hardness of flexible calendared sheet in durometer, it turned out that the content of CPVC resin in the blend increases the softness of the product the more CPVC is being added. This property ultimately allows the reduction of plasticizers in the formula. CPVC has an LOI limiting oxygen index of 60. That means a product made from CPVC requires 60% oxygen in the environment in order to sustain a flame. Since our environment only contains around 20% of oxygen, CPVC has self-extinguishing properties and improves the flame retardancy properties of the calendared sheet. This flame retardant property of CPVC is also the reason why 100% CPVC pipework is allowed in fire sprinkler applications in building construction. It is important to note, however, that other additives contained in the recipe will impact the level of the LOI, so that it might be lower than what is referred to in standard literature with regards to UPVC. In this case, the LOI was tested comparing 100% PVC containing antimony trioxide as a flame retardant additive to a 60-40 PVC CPVC blend. The application formula was designed for cables containing antimony trioxide. The LOI of the blend reached 34, while standalone PVC showed an LOI of 30. Another important factor judging the fire behavior is by measuring the optical smoke density. The optical density is usually obtained by measuring the attenuation of a light beam passing through the smoke, in this case according to ISO 5659. Barium zinc-based systems nowadays have the majority of the European market share for stabilization of PVCP due to extensive formulation development based on increasing the barium content and the important role for new and existing organic co-stabilizers. In this case, following blends were tested for comparison. 100% PVC containing 40 PHR plasticizer, a 70-30 PVC CPVC blend, a 70-30 PVC CPVC blend containing 3 PHR barium zinc, a 70-30 PVC CPVC blend containing 30 PHR of the flame retardant additive alumina trihydrate. While the sheet made from standalone PVC showed a smoke density in density meter (dm) of more than 1,000 kilowatts per meter square, the density of the different blends containing CPVC resin varied between 550 to 680 kilowatts per meter square. The average speed of smoke appearance within the first 4 minutes for the 100% PVC product was 2,090 kilowatts per meter square, while again those values were considerably lower for the PVC CPVC blends, from 960 to 1,560 kilowatts per meter square. Fire retardant flooring and wall systems. Being often part of building construction, those applications have to comply with severe safety regulations, which can vary between different countries. Often, standalone PVC will not be able to comply with the requirements when it comes to heat resistance, flammability properties, and low smoke release. Fire-resistant retardant power cables. These applications call for PVC formulations with considerably higher fire retardant requirements due to the highly demanding nature of the application. When printing films, the addition of CPVC to the blend can be a good technical solution to improve the printing quality. On top of that, depending on the application area, national standards also require fire classification, i.e. low flammability. For example, the electric burner test of the French national standard, NFP 92-503-505, requires the highest one out of 4 possible classifications, which is M1. To achieve an M1 classification, the combustion duration of the tested material must not exceed 5 seconds. It is not allowed to show any damage in length and width and may not produce droplets. The Germany national standard, DIN 4102, requires the classification B1, i.e. the mean residual length of the test specimen must be less than 150 mm, does not show complete burning, and the mean smoke gas temperature is less than 200 degrees Celsius. According to the literature, the M1 and B1 classifications are interchangeable, meaning if a test specimen achieves M1, it will also achieve B1 and vice versa. The flame retardancy of foamed extruded sheet can be increased by adding CPVC to the blend, including blowing agents. When doing so, the LOI of the 9010 PVC CPVC blend was measured to be 42, while the LOI of the PVC blend containing antimony trioxide flame retardant was 41 and PVC standalone 36. Neither an influence on the foaming behavior nor any effect on the sheet extrusion processability was observed. The addition of CPVC to a PVC blend helps to improve the thermoforming capabilities of sheet. On the left, you see the deformation at break, comparing PVC to CPVC sheet. On the right, thermoforming was measured with a 2 mm thick sheet at a pressure of 3.5 bar and a temperature of 140 degrees Celsius for PVC, and 155 degrees Celsius for CPVC. As the comparison shows, the thermoforming depth for PVC was 40 millimeters, while for CPVC it was twice as much, 80 millimeters. Foamed sheets are used for advertising panels, which need a high fire resistance despite varying national requirements. Ratings achieving the classification BS1D0 according to the European standard EN 13501/1 are possible when adding CPVC as it improves the flame resistance. The rating BS1DO is used to classify combustible materials installed in public buildings and expresses that the product material has very limited contribution to fire. The less severe rating, CS1D0, is used to classify combustible materials installed in private office buildings, and the requirement can vary by country. It expresses that the product material has limited contribution to fire. If you would like to receive more information on CPVC technology or would like to trial a sample, we are here for you.